A sudden idea, a flash of intuition, or a gut feeling that seemed to appear out of nowhere, something that makes you stop and think, wait, how did I know that? It feels almost magical, like your brain suddenly unlocked some secret code and handed you the answer. But what if I told you that this magic isn't magic at all? It's math. Invisible, constant math running inside your brain every single second of every single day. Welcome to Psychomath. I'm here to break down the connections between mathematics, biology, and mental health. And today we're going to decode neural networks, the interconnected system of neurons in your brain that produce thoughts, creativity, and intuition. Over the next 20 minutes, we'll explore the biology behind these networks, the mathematical principles that govern their activity, and how the structure naturally produces those flashes of insight and creative ideas that feel so mysterious. By the end of this video, you'll understand why your mind can seem like a supercomputer, constantly performing complex calculations without your conscious awareness. You'll see that intuition isn't mystical, it's mathematical. Creativity isn't random, it's combinatorial. And your brain isn't magic, it's a living network doing incredibly sophisticated math in real time. So let's dive in and decode the neural networks that make you, you. Let's begin with the most basic building block of your brain, the neuron. Your brain contains roughly 86 billion of these cells. Each one is surprisingly simple on its own, but when connected together, they form networks capable of astonishing computation. As you can see here are the dendrites. A neuron receives signals from other neurons through these structures. Think of them as input channels. All these signals go through here. This is the input in which they all go through. So it goes through the axon and then out through the axon terminal. So they all come in through a synapse. That's these little connection points that you can see right here. And they each carry some information. Here's the key. Some of these input signals are excitatory, which means they push the neuron towards firing. Some others are inhibitory, meaning they hold it back. So you can see all of these multiple dendrite paths through the stoma. These pluses over here, some come from minuses, some come from a single plus. The neuron doesn't just react to one input. It integrates all of the incoming signals. It adds them up. Every excitatory signal adds to a running total, and every inhibitory signal subtracts from it. The neuron is essentially performing a calculation, a weighted sum of all its inputs. Inside the cell body, you can see the soma over here. In this soma, the calculation is compared against a threshold. If the total sum of inputs crosses the threshold, the neuron fires. It sends an electrical signal down this long structure called the axon. And here you can see the signal, which then goes to the axon terminal. The signal then reaches the other neurons, continuing the chain reaction. So there's a neuron over here. Another piece of the neuron will be like right here. So this would be the dendrites over here. And you had a soma right here. And then another axon. And then multiple dendrites are branching out. So as you can see, this axon terminal has the connection points. This is the synapse. This is the place where the information gets transmitted. But if the sum doesn't reach the threshold, the neuron stays silent. It's binary. You have zeros and ones. You can either fire or no fire. 1 or 0. Yes or no. There's two options. At first glance, this might sound overly simplistic. How can something so basic create thoughts, memories, emotions, and consciousness itself? The answer is scale and connection. One neuron alone doesn't create thought, but billions of neurons, each making yet the tiny yes or no decisions based on weighted sums of inputs, collectively produce emergent behavior, perception, memory, decision making, emotion, creativity. All of it rises from this simple mechanism repeated over and over again across billions of cells. So as you can see here, if the sum of inputs is greater than the threshold, then it will fire, then it will move to this neuron, and then it will move to another neuron, and it will continue moving. It's a chain reaction until the sum of inputs is not greater than the threshold. Mathematically, you can describe a neuron's behavior with this simple inequality. The weights represent how strong each connection is, how much influence one neuron has on another. Strong weights mean a signal has more impact. Weak weights mean less impact. So as you can see here, the synapses over here, these little points are the information places. These weights aren't fixed. They change over time based on experience. When you learn something new, certain synapses strengthen while others weaken. This is called synaptic plasticity. Right here, the biological foundation of learning and memory. This is how these synapses change. This is how your brain changes when it grows. Others strengthen, others weaken. This is a key fixture in Alzheimer's disease. The strengthening and weakening of these synaptic end bulbs and the tau protein. This is all integrated in your brain. Look at this big neuron. Let me emphasize this again. A neuron doesn't think in isolation. It doesn't have awareness or intent. It simply applies a rule. Sum the inputs, compare it to the threshold, fire if necessary. That's it. But string billions of these together, layer them in complex arrangements, connect them in intricate patterns, and suddenly you get a system capable of abstract thought, intuition, and creative problem solving. This is the foundational principle behind both biological neural networks in your brain and artificial neural networks in computers, which we will go to next. Let's look at these neural networks. Now let's scale up from a single neuron to a network of neurons, because one neuron alone can't produce thought, but millions of them layered together form what we call neural networks. And these networks can do something remarkable. They can detect patterns. That was supposed to be a dramatic silence. So as you can see at the input layer, neurons in your brains are organized into functional layer. The input layer gets the information from your senses. You're seeing those photons hitting your retina become electrical signals. The sound waves on your tympanic membrane become signals. The touch receptors in your skin become signals. Your gustatory taste becomes signals. Your olfactory smell becomes signals. All of this sensory data enters the network as patterns of neural activation. All of these senses are going in here. You got your taste, you got your sight, you can see, you can taste. Wait, no, that's not a tongue. That's a tongue. And then this is an eye. You can see, taste, all of these inputs go into this inputs layer. All of these sensory data enters it as the patterns of neural activation. This activates the entire chain reaction. Then we have the hidden layers. Woohoo! These are layers of neurons that sit between input and output. They transform the raw sensory data, extract features, and detect patterns. One layer might detect edges in an image. Others might detect shape. Another might recognize objects. Each layer builds on the previous one, creating increasingly abstract representation. So you have the sight. Okay, what if you see a person? I see a person. What does the hidden layer detect? Maybe the hidden layer might detect the face. Or maybe it might detect the legs. This is the hidden layer. It creates more increasingly abstract representations of what you see, of what you taste, of what you hear. And then finally, we have the output layer, which gives us our result. This could be a thought. That's a face. It could be a movement. Reach for that object. It could be a motion. This situation is dangerous. The network has taken raw input, processed it through multiple transformations, and produced a meaningful output. Your thoughts. This is what you think. It comes right here from what you feel, from what you see, from what you taste. And then it gets exact visualizations, abstract representations. And then it outputs it as thought. This is what you think. This is in your head going billions and billions of times a second. This is literally amazing. So let's animate it. Okay, so we're gonna get a random signal coming in from the input layer. Let's say you're looking at a picture of a dog. This is my dog. A really cute dog. Okay, so we have a picture of our dog. and then you see it. Okay, so it's with sight. The photons hit your retina, and then it goes into the inputs layer. Neurons in this input layer activate in response to light patterns. These neurons send signals to the hidden layer, where some neurons fire strongly because they detect edges, other fire because they detect fur texture, these little furs, these edges. Others fire because they take shapes that look like ears or a nose. Look, you see the little nose over here. Ears. They all fire for different reasons to create an output. Then these hidden layers send it forward to the output layer. And another hidden layer might even combine these features. Edges plus the fur plus the ear shape equals a dog. Finally, the output layer produces the recognition. Dog. Your brain has classified the image. This is machine learning. This is how you learn. You look at it, it makes representations of it based on what you already know to create a dog. You have classified an image. Congratulations. Now, here's what makes neural networks so powerful compared to traditional step-by-step programming. They are pattern detectors, not rule followers. A traditional computer program would need explicit instruction. You have to tell it to do something. If a shape equals X and a color equals Y and a size equals Z, then output dog. No. Neural networks do it differently. It learns patterns from examples. Show it thousands of dog pictures. You have 1,000 times of these. And then it'll get dogs on the first try. It learns from previous experiences. And it learns the underlying patterns that make something a dog, even if it's a breed it's never seen before. It knows that these ears make it a dog, these legs make it a dog, this fur texture makes it a dog. These all things make it a dog, even if it hasn't seen one yet, because it knows how dogs look from before. It's the patterns. The brain is a pattern machine. Your brain is fundamentally a pattern machine. That's why you're incredibly good at recognizing faces. You see faces. You see them every single day of your life. They're walking along the street and you look at them and you say, hey, I know that guy, because you've seen faces before. You understand language even if you might not even know it yet. Think about it. Every language basically has the same word for mother. It's just starts with an M and the rest is something else. You know that because you've heard languages that start with M and have the rest as something else. You know it because of the patterns. You know that there's always gonna be this M. Picking up melodies, you can hear the songs, you can know the genre, you can know it's rap if it's saying random words at 500 speed, and you can read emotions because you know their facial textures. Look at this chiseled face, I'm telling you. All these things involve complex patterns, but you're relatively bad at exact calculations, like multiplying 3-digit numbers in your head. That's not pattern detection, that's rule following. These are mathematical rules that humans have invented to explain our understanding of the universe. That's not pattern detection. And that's not what your neural networks evolved to do, which is why you probably can't do 67 times 67 in your head really fast. So, let's look at the connections behind layers. The math behind this is just weighted sums and thresholds like I discussed before. Each neuron in the hidden layer receives weighted inputs from the layer before it, sums them up, compares it to a threshold, and fires or doesn't fire. Then those outputs become inputs to the next layer. Simple math, repeated millions and millions of times across many layers, produces incredibly sophisticated computations. This is what we are. This is what makes us human. And here's the truly amazing part. You're not consciously aware of any of this happening. It's all in your head. Right now, as you watch this video, your visual cortex is firing millions of neurons in layered patterns to extract features from the image on your screen. Your auditory cortex is doing the same with the sound of my voice. Your language centers are parsing the meaning of my words. My words are just sound, but you have heard words before, so you know what they mean. All of this is happening automatically beneath conscious awareness through neural networks performing massively parallel pattern detection. This is the computational substrate of your mind. And let's talk about intuition. Because this is where neural networks start to explain something that feels almost supernatural. How you can suddenly just know something without consciously thinking it through. Intuition is your brain's ability to recognize patterns instantly. You go from A to B like as fast as a snap, speed of light, without conscious deliberation. When you have a gut feeling about a person, a situation, or a decision, your brain isn't guessing randomly. These are calculated decisions based on past experiences stored across millions of synaptic connections. Your neural networks have already encountered similar patterns before. You've seen this person. You know this dog. It's a cute dog. And you can predict the most likely outcome almost automatically. And here is conscious thinking. This is different. This is deliberate reasoning. This is slower, but step by step. When you consciously think through a problem, you're using your working memory, following logical steps. You go from 1 to 2 to 3, and then to 4, and onwards and onwards. You're considering alternatives sequentially. That's why you're going here. Maybe I should go here, or maybe I should go here. All the alternatives. This is slower, but more flexible and controllable. But intuition takes a shortcut. The networks have already learned the pattern, so they can jump directly from input to output. You see someone's facial expression and instantly feel that they're untrustworthy. That's pattern recognition. You look at a chessboard and immediately see a strong move. That's pattern recognition. You walk into a room and sense social tension. That is pattern recognition. Oh. All intuition. But here's what happened neurologically. Certain patterns of neural activation have been strengthened through repetition and experience. When a similar pattern appears at the input layer, it activates a cascade through the network so quickly and efficiently that the output appears before you've had enough time to consciously process it. The signal races through well-worn pathway, through neurons whose connections have been strengthened by past experiences. It goes through all these yellow circles. It bypasses it. It's like the expressway. You may get to your destination, but you'll get there faster. And it might not be the way you want to get there, but you will get there in the end. And you will pass it. And it may not be correct, but you will do it faster. But you can't always rely on it for everything. It is fast pattern recognition, but it does improve with experience gained from conscious thinking. A chess grandmaster has trained their neural networks on thousands of positions. A doctor has trained their diagnostic intuition on thousands of patients. An artist has trained their aesthetic intuition on thousands of hours of practice. The more examples your networks see, the better they become at recognizing patterns and making rapid predictions. But here's the trade-off. Like I said, intuition is fast, but inflexible. It's excellent when the pattern is familiar, but can fail when the situation is genuinely novel. Like you literally see something you haven't seen before. You see dog poop on the side of a road. Look at that stuff. You see that. You don't know what it is because you've never seen dog poop. I mean, I don't think you have. But then you just saw it, and that's new. You don't know what it is. That's why some experts sometimes make intuitive errors in unfamiliar situations. The networks are matching to the closest pattern they know, even if it's not quite right. Corona looks like corona, but it's actually a mean disease. It kills you. COVID is bad. But conscious thinking is slower, but more adaptable. You can deliberately consider unusual scenarios, override your gut feelings, and think through situations that don't match your past experience. Both systems, intuitive and deliberate, are valuable. They work together in your brain, with intuition providing rapid assessments and conscious thinking allowing you to override or refine those assessments when needed. And then they work together. In fact, the best decision making often combines both. Let your intuition offer quick pattern-based insights, then use conscious reasoning to evaluate whether those insights make sense in the correct contexts. Trust your gut. That gut right there. Over there. But verify with that brain. Yay. Let's combine patterns to make new ideas. Let's talk about creativity, because this is where neural networks reveal something beautiful about how new ideas are born. Creativity isn't random inspiration from the universe. It's your brain connecting patterns in new ways. Look at this idea. This is a pattern or a concept you've learned, maybe a mathematical technique you know from calculus, like integrals. Oh, those are so ugly. I hate integrals. Or differentiation. This is a new thing that you've learned. And then you get a new idea. This is a completely different pattern, maybe a biological process, like how cells divide, how 1 goes to 2. Boom, division. Mitosis right there. Cytokinesis, all the random bio stuff. I don't like it. And then arrows from both ideas converging to the new idea circle. They combine. They make a new idea. Woo-hoo. Creativity happens when your neural networks find connections between these previously separate patterns. Maybe you're studying population growth and suddenly realize it follows the same mathematical curve as compound interest, that J-curve. Or you're working on a design problem and realize a solution from nature, like how termite mounds regulate temperature, could inspire your building's ventilation system. The moment of insight, the aha feeling, is neural networks from different parts of your brain firing together for the first time. You're not creating something from nothing. You're recombining existing patterns in novel ways. Creativity is the new combinations of old patterns. It requires a broad base of knowledge. The more patterns you have stored in your networks, the more potential combinations exist. Steve Jobs famously said, creativity is just connecting things. He was describing exactly this neural process, finding unexpected connections between diverse experiences and knowledge. But here's what's interesting. These connections don't happen through conscious effort alone. Your brain needs to be in the right state for distant neurons to interact. This is why creative insight often comes when you're not actively trying. In the shower, on a walk, right before sleep, your brain is in a more diffuse, associative mode rather than a focused, directive mode. During relaxed state, your brain shows more widespread, lower frequency neural activity. Networks that don't usually talk to each other start exchanging signals. A visual pattern might connect with a verbal concept. These unexpected collisions of patterns are the source of creative ideas. Look at these neural networks diagrams. Remember this? During focused thinking, signals pass through organized paths through specific layers. During creative thinking, they jump between networks more freely. It's like the difference between walking on a sidewalk versus cutting through a field. You discover a path you never knew existed. Wow. This is also why diverse experiences enhance creativity. Every new skill you learn, every new book you read, every conversation you have adds new patterns to your neural network. And each neural pattern is a potential building block for future creative combinations. The mathematician who studies music, the programmer who paints, the biologist who writes poetry, they're all increasing the diversity of patterns available for recombination. So the next time you have a creative insight, recognize what's actually happening. Your brain has successfully connected two patterns that have always been there but never interacted before. Creativity is pattern recombination, powered by flexible neural networks. It's not magic, it's mathematics, meeting biology in the exact right way. Now let's talk about mental flexibility, and we're gonna end it soon. Before we close, I want to talk about mental flexibility, because understanding neural networks isn't just intellectually interesting. It has practical implications for how you think and learn. This is the original network, one where signals follow the same paths over and over again. It's a loop. You go on and on and on, and every time you encounter a similar situation, your brain activates the same loop, on and on and on. This is efficient for well-practiced skills, but can also trap you in repetitive thought patterns, because you go on and on and on. And when this becomes excessive, it can contribute to overthinking, rumination, or anxiety. You're absolutely cooked. So just like pack it up right now. Your neural networks keep firing the same patterns every day when they're not even helpful. The same worries keep on going on and on and on. But there's a way out. Flexible patterns, signals branching in new directions, exploring different paths and forming new connections. This flexibility is what allows learning, adaptation, and creative problem solving. Neuroplasticity is that networks can change. This is good news. The ability to rewire itself throughout your life. Synaptic connections can strengthen or weakness, like I talked over here. Look at this. This is the point where it all meets. This is the point where it changes. Old patterns can fade. Your neural networks are not fixed. They're dynamic and responsive to experience. Look at them. They're branching out. They're moving. They're learning new stuff. They're evolving. They're saying 6, 7, and 41 because that's the meme. That's what's trending. They're moving. They're evolving. They're being so cool. So how do you build more flexible networks? First, expose yourself to novel experiences. See new things. Do new stuff. You'll learn new things. You'll have more branches. Second, try doing different approaches to problems. Try adding 1 plus 1 by doing 2 plus 0 instead of just doing 1 plus 1. You know, it's the same way, but you got the same answer but a different way. Look at it. The Holy Grail. Third, engage in activities that require creativity and improvisation. Do something new and things that require you to think. Like use that head of yours. Come on. Use that head. You got it. But both patterns are still good. Rigid patterns are automatic. Like, you can type. You know the QWERTY keyboard. QWERTY, TY, U, I, O, P, AS, D, F, G, H, J, K, L. You know it. It is automatic and you can easily write it. And flexible patterns help for adaptation, learning, and creativity when you need them. So, all these diagrams explain one thing. Your brain is extraordinary. Oh my god. 86 billion neurons, each one following simple mathematical rules, summing weighted inputs and firing when thresholds are reached. But these simple rules, repeated across billions of cells organized in layers, produce something remarkable. The ability to detect patterns, recognize familiar situations, and generate novel combinations. At the foundation, we have individual neurons performing basic calculations, layered networks, familiar patterns making intuition, different domains, new ideas, creativity. Understanding the math and biology behind neural networks does not diminish the wonder of consciousness. It deepens it. Every flash of insight shows you something new, creates the extraordinary phenomenon that is your mind. So the next time that you have a sudden idea, remember that your brain isn't magic. It's way more impressive. Way more impressive. This is Psychomath, where we decode the connections between mathematics, biology, and the human mind. If you found this fascinating, there's so much more to explore. How learning actually changes your brain structure, why anxiety can trap you in thought loops, how sleep recognizes your neural networks, and how artificial intelligence is inspired by these same principles. Thank you for watching Neural Networks Decoded. If you like this lesson, please hit a like, comment, or subscribe. I'll be happy to know your constructive criticism, but please make sure it's constructive. Please. And by the way, this is my first video, so let me know in the comments, what do you think? I'll be posting once a week from now on, so stay tuned. Your brain just used brilliance of neural connections to understand neural connections. That's pretty amazing. Is that a paradox? I'm confused. I'll see you in the next video. 6-7.